excuse me, then we'll leave Vesta, travel almost an additional 3 years to reach Ceres. And at each of these targets, Vesta and Ceres, we'll make a comprehensive set of measurements. We'll get color photographs. Everybody likes to see that, of course. We'll also compile a topographical map. That'll be interesting both here at the south polar crater at Vesta, and that'll tell us a lot about whether or not Ceres really is composed of water and ice. We'll map the elemental and mineralogical composition. That is, what are the individual elements that make up these bodies and how do they combine to form rocks and minerals. We'll measure the gravity field, which will tell us something about the interior structure of the bodies, and we'll search for moons. And so with this comprehensive set of measurements on 2 different bodies, it really makes Dawn truly unique because this is a mission of comparative planetology. And we have never before attempted to send a spacecraft into the solar system to orbit 2 different bodies. But why is that? Scientists have been interested in a mission like this for many, many years. But why is it that we've never tried something like this before, never tried to orbit 2 bodies? Well, I'm glad you're wondering why it is, because I'm going to tell you. And that is, until very recently, engineers and scientists who wanted to do this were confronted with a problem. And they're confronted with the same problem that these 2 gentlemen have. That is, we just don't have the technology to carry it out. Excuse me. Let's take another look at the solar system and try to understand why that is. Here again is the same picture I showed you before, the orbits of the planets. And I didn't mention earlier that we talked about where you could see Jupiter and Saturn. Now that we have this zoomed-in view, you can also see Venus setting in the evening sky, at least when it's not cloudy, like it is today, setting in the evening sky just shortly after the sun does, because Venus, as viewed from Earth, isn't that far here from the sun. But back to the problem at hand here, we want to get from Earth way out, even past Mars, to catch up with asteroid Vesta. That's a long way to go. And I think people often don't appreciate that it's much more difficult to go into orbit around a distant solar system body than it is just to fly by it. Because we have to get the spacecraft way out here, and then we have to match Vesta's orbit around the sun. So we have to send a spacecraft out here, in some sense sort of stop where Vesta is, and then go around the sun with it. That takes a lot of maneuvering by the spacecraft. But it's more difficult than that, because once it's done that, then the spacecraft on its own, without the help of a rocket, has to leave Vesta and travel to still another part of the solar system, get out to Ceres, and then do the same thing there. It has to travel out to Ceres, stop there, and go into orbit and follow it around the sun. And it turns out it's more difficult to get into orbit around bodies that don't have a large gravity. So when we send spacecraft, for example, to Mars or Jupiter, the gravity of those planets, in some sense, helps pull the spacecraft in and bring it into orbit. And while we saw Vesta and Ceres are the largest asteroids, they still don't have enough gravity really to help this process very much. And so that means the spacecraft has to do a lot of the work. But it's still more difficult even than that. And to understand why, I want to give you a different perspective. Here we're sort of looking down on the solar system. I want to now switch views, so we'll be looking in the same plane as most of the planets are orbiting, and we'll look from down here. So now you can see here's the orbit of Jupiter, and the other planets are all in here, nearly in the same plane. But Vesta and Ceres are not. You can see their orbits are tipped. And it turns out it's very difficult to change the plane of the spacecraft's orbit around the sun. And you can understand that by imagining that if you're driving in a car at very, very high speed and you try to turn, well, I should remind you, when the spacecraft starts at Earth, it's going at high speed because Earth is zooming around the sun. Now we want to turn the orbit, tip it like that. When you turn your car, unless you have a banked road, you have to slow down, put on the brakes, turn, and then speed back up. Well, all of that work, the putting on the brakes and the speeding back up, all that sort of thing has to be done by the spacecraft. And so all of this getting out to the this distant part of the solar system, stopping there, meeting up with the body, changing into its orbit around the sun, tipping the orbit. That takes a lot of maneuvering by the spacecraft. And again, until recently, we simply haven't had the technology to do it. And so the question that we've asked is simply, how can we travel around the solar system more easily and less expensively? And the answer to that, which is familiar to many science fiction buffs, is ion propulsion. And without it, we simply would not be able to do a mission like Dawn. Now, if you're like me, and I know some of you are, the first time you ever heard of ion propulsion was in science fiction. In fact, the Star Wars TIE fighter, TIE means twin ion engine. And the first time I ever heard of ion propulsion actually was in Star Trek, the original series. And there are several episodes that refer to ion propulsion. One in particular where Mr. Spock, in describing an alien ship, refers to the ion propulsion as high technology, advanced technology, high velocity. Scotty sort of drools over this incredibly cool ship and says they could teach the Enterprise a thing or two. And Captain Kirk points out that advanced ion propulsion is beyond even our capability. And so ion propulsion has been in the world of science fiction for a long time. And part of the reward of many of us working at a place like JPL is getting to turn that science fiction into science fact. So let's take a look at the fact of ion propulsion. Let me first remind you how a conventional propulsion system works. You take a gas and you heat it up or you put it under pressure and you push it out of a rocket nozzle, and the action of the gas leaving the nozzle causes a reaction that pushes the spacecraft in the other direction. And it's much the same thing happens if you have a balloon and you let go of the open end. As the air is pushed out from the pressure of the elastic in the balloon, the air being pushed out is what pushes the balloon in the other direction. Well, ion propulsion works the same way, but we don't heat the gas up or we don't put it under pressure. First of all, we begin with the gas xenon, which is like helium or neon, but heavier. And we introduce it into a chamber here, which is about a foot or so in diameter. And then we bombard it with electrons. It's very much like the electrons in your television set that light up the screen. And perhaps you recall that atoms, of one kind of which is xenon, consist of a core of positively charged protons along with some neutrons, surrounded by a sort of a cloud of electrons. And there are just exactly as many positive protons as there are negative electrons, so it's electrically neutral. But when one of these electrons hits a xenon atom, it'll knock off an electron. So this electron goes this way and it knocks another one off. So now we have an imbalance. There's one fewer electrons than protons, and so we're left with a net positive charge, and that's called an ion. And the importance of this is when it's ionized or charged, it can respond to a voltage. It can feel the effect of a voltage. And so we have two grids here that are separated by just a very small amount, about 6 or 10 times the thickness of a human hair. We'll put a large voltage on them, and they accelerate the xenon ions and shoot them out to the right at very high speed, 35 kilometers per second, or well over 70,000 miles per hour. And the action of every ion going off to the right causes a reaction that pushes the thruster and the spacecraft that it's attached to the left. And so that's how the ion propulsion works. We shoot these xenon ions to the right, and they push the spacecraft to the left. And here's a photograph of a thruster operating in a vacuum chamber, and it does produce this nice sort of blue or bluish-green glow like you see in the science fiction movies. And the reason for that is it glows blue. Xenon glows blue just as neon in neon lights glows orange. Now, the trick is that although this is extremely efficient, the thrust is very low. And the reason for that is we flow just a very small amount of xenon through the thruster at any one time. In fact, we flow so little through that it would take days to use up just